Okay, so on Tuesday, I started the accelerated climb flight. Before that, we were doing the steady flight. I'm sorry, the steady steady climbing flight. So in that case, our assumption was that we have an aircraft that climbs at a steady rate. So let me just find that. Okay, so we said that the speed of the aircraft is constant, and the difference between this case and the steady level flight is there's a non-zero, there's a positive flight path angle. And then by manipulating the drag equation, we arrived at this equation. So we basically obtained an expression for the vertical speed of the aircraft, which we call the rate of climb. So from this equation, we see that rate of climb depends on what we call excess power. Okay, and this is the power supplied by the engine and the power consumed by the flight, difference between the two. So we can get this information directly from the power curve. So the power required curve looks something like this. And normally in a steady level flight, the power produced by the engine should be equal to the power of the flight. So we should be flying at an intersection point between the available power and the required power. But if the available power is more than the required power, something like this, for example, this is your flight speed, and your engine produces this much power, whereas the flight requires this much power. So this difference here gives you the excess power. Okay, so if you just calculate this number and then divide it by the weight of the aircraft, you can directly calculate the vertical speed of your aircraft. And then we started a more general case where the speed doesn't have to be constant. So we just use the same force diagram. The forces are exactly the same as before. The only difference is instead of equating the sum of forces in this direction to 0, we equate it to mass times acceleration. And from here, we obtain this relation. On the left, we have the specific excess power, which is the excess power divided by the weight. That's equal to the vertical speed plus this term, which is related to the forward acceleration of the aircraft. And so from here, the concept of energy height is defined. So this is related to the altitude of your aircraft, and the other term is related to its speed. So if you have additional power to your aircraft, this power can increase its potential energy or kinetic energy, or it can affect both of those energy terms simultaneously. So if you write the total energy including the potential and the kinetic, and if you divide this by the weight of the aircraft, you get an expression for specific energy. So this is the total energy per unit weight of your aircraft. So this expression is your energy height. Okay, so this includes the actual altitude and this second term, which also has the units of height, and this is called the total is called the energy height of an aircraft. So if you look at the total energy height term, you have, this is basically the sum of two terms, right? So if your total energy height is something, then some of that total energy is due to this and the other part is due to this. So from here you can draw constant energy height contours. So the blue curves you see on this graph are constant energy height contours. So at every point on this curve, for example, the total energy height is 6,000. But on this end, where the speed is 0, the entire energy height is composed of actual height. But if you come to this end, the actual altitude is 0, and the total energy height is still 6,000, but that 6,000 entirely comes from the kinetic energy of the aircraft. Okay, And then the last thing I did on Tuesday was I gave you this example. So let me remind you what that example was. We were considering an aircraft that takes off at sea level with an initial velocity of 80 meters per second. And after some time, it reaches its final altitude of 11 kilometers. And when it reaches that altitude, its speed also increases to 250 meters per second. So if you look at this, both the potential energy increases going from here to here, and its kinetic energy increases as well, right? So its speed increases from this value to that value. So we can analyze that climb on a total energy, a constant energy height contour plot. So the initial point corresponds to this point. The actual altitude is 0. The speed is 80. When it comes to the final flight altitude, it has a speed of 250 meters per second at 11 kilometers altitude. So it goes up from this energy level to that energy level. Okay? Okay, so before I proceed from here, let me just explain you the connection between the plot we saw earlier and this new plot. Okay, so these are constant energy height contours, but not every point is a flyable point, right? So what I mean by that is so we were talking about power versus speed curves, right? So if this is your power required curve, and if this is a let this be a propeller aircraft. So in that case, the available power will be a flat line. So this is PA maximum. So at this altitude, the aircraft can fly only within a certain speed range, right? So this is the maximum speed at this altitude, and the minimum speed will either be determined by the stall speed. Let's say this is the stall speed, or if stall speed is really low, then the minimum speed can be limited by the power. So this is V min due to power. So that means the aircraft can only possibly fly at a certain speed range. Okay, so it cannot fly faster than the maximum speed. So this is an out of the range of this aircraft's flying speed range, and similarly there's a lower limit. So what this means is if you come to this curve here, let's say let this be the condition for this is at h is equal to 2 kilometers. So you come to this plot. Let's say this is the curve for 2 kilometers. The aircraft can only fly within the certain speed range, right? So there will be a minimum speed. Let's say this is the minimum speed, and the maximum speed, and let this be the maximum speed. Only this part is flyable. Okay, so the aircraft cannot fly outside that speed range. If you do find this valid speed range for different altitudes, you will find something like this. For example, you do the same for 5,000 meters, and then you do the same for all a number of different altitude levels, and finally you will get an area that shows a valid flying speeds. So I'm just making it up right now. I don't really have an exact curve for a real aircraft, so I really apologize for that. But so anyway, in the end, it will look something like this. Okay, so that means on this constant energy contour plot, only that area is a flyable area. and this will correspond to the absolute ceiling of your aircraft, right? So this is the the absolute ceiling, and this is the corresponding speed for that. So this is what I was referring to at the beginning of the class. But you can find an exact area by writing computer programs. And in fact, I will ask you to do that. I will give you some sample data for some aircraft, and I will show you some computer codes. You've taken Fortran, right? So you know how to program in Fortran at least. And I recommend MATLAB. MATLAB is a much easier way of writing a code. So you can, for this sample aircraft, you can find an exact area, and you can say that this is the flyable area for this aircraft. Okay, is this clear? So, for example, so remember when I explained the absolute ceiling, I said you come to an altitude where your required power is like this, and your available power is this. So there's only one point where your aircraft can fly. So that point corresponds to this point here. Okay, so there's a certain speed, and then that corresponds to a certain altitude. So one thing worth mentioning here is in the example where we have an aircraft that takes off here and reaches the final point here, there is no single way of going from there to there, right? So I show you two special cases here. The first one is the red path. If you look at what the aircraft does in this red path, it starts climbing at a constant speed, right? So in the first part of the flight, the speed doesn't change, but the altitude changes, and it reaches the final altitude. So there it performs an unaccelerated climb, and then once it reaches the final altitude, it starts accelerating. It goes from then in the second part of the flight, the altitude doesn't change, but the aircraft accelerates from this level to this speed to this speed. So that's one way, one special case of performing that climb. And in the second special case, it follows the green path. What it does in that case is, first it starts accelerating, right? It takes the entire excess power, and it uses that to accelerate from the initial speed to the final speed at the initial altitude, and then it starts climbing. At the final speed, it climbs from here to there. So this is another special way of doing this climb. Or the more reasonable thing to do is to increase both energies simultaneously, right? Something like going through this blue path. So it starts climbing while at the same time accelerating, and then it reaches the final point that way. So there are infinite possibilities, and it all depends on the pilot how to perform this climb. Well, in this course, really, we don't say anything about how the pilot chooses which way to follow. But you should know that there are infinite ways of performing such a climb, and the general equation that you can use if you want to analyze this properly is the accelerated climb equation I showed in the last lecture, which was this equation. Okay, so this equation can be used to study different climbing flights. Oh, by the way, if you do something like this, then you may very well see that these two special climbs are not really possible. So if you copy this and bring it over here, okay, so let me change its color. So it will most probably be something like this. For example, you cannot really climb to 11 kilometers by keeping your speed constant at the initial speed, because you'll be out of this flight envelope. Or you cannot really do this path either, because the initial you cannot reach this speed at zero altitude, because it will be higher than the maximum speed of that altitude. So you have to always stay within this envelope. Okay? Well, I know that these things may look, I'm sure you understand what I'm talking about, but only after you start doing something with these diagrams and with these equations, you will understand what these are all about. So I strongly suggest that once I give you those example codes, just play with them and try to get some useful data like this. And after that, I'm sure you will have a full understanding of what all these diagrams are all about. Okay, now there's a very simple example here related to the accelerated flight equation, this equation. Okay, so let's say we have an aircraft which flies at sea level at a speed of 100 meters per second, and the pilot has some excess power of this much, 100,000 watts, and the weight of the aircraft is 10,000 newtons. So using this data, we can calculate the excess power. Well, the excess power is already given, but the specific excess power is excess power divided by the weight. So for this aircraft, we have the specific excess power is 10, and the unit of this is meters per second, because it's the right hand side is has units of meters per second. So first we are asked to calculate the rate of climb of the aircraft if it performs unaccelerated climb. So the right hand side should be equal to this, and if the climb is unaccelerated, then this part will be 0, and the rate of climb will be equal to the specific excess power. So in that case, the rate of climb will be 10 meters per second. In the second part, we are asked to find the acceleration if the entire excess power is used for acceleration at constant altitude. So in the second part, the altitude is given to be constant. So this time, this term is equal to 0. And the acceleration, so this entire specific excess power is used for acceleration. So we just get rid of this term. This is 0. And then we find out that the acceleration is given by 10 times g over v, and since v was 100, it turns out that the acceleration is going to be 0.1 g. Okay, so the same aircraft, the same excess power, but this time instead of climbing, the pilot uses that for acceleration. So in addition to this, we can also assume that so in the last case, let's assume that the pilot starts climbing at, well, the aircraft starts climbing actually, climbing at a rate of 5 meters per second, and the rest of the excess power is used for acceleration. And what will be the acceleration? So the excess power is still the same, 10. So this part now is equal to 5. So we are asked to find this. So we can easily conclude that the acceleration in that case is going to be 0.05 g. Okay. So this is exactly equal to, right? Why? I don't know why I said approximately equal to. Okay. So I talk about three cases, right? Those three cases are, if you want to show them on this plot, the first one will be, it was climbing at fixed constant speed, right? So the first one was going in that direction. And the second one, it was going through this direction. And in the last one, it's going in the middle, right? It's going, starting with in this direction, that some of the excess power is used for climbing and some is used for acceleration. Okay, I think we can continue, right? Is there anything you want to say? Şimdi videoyu seyreden kişi tabii bir sınıfı görmediği için böyle büyük bir sınıf var zannediyor olabilir. Oysa ki şu anda 5 kişiyle ders yapıyoruz. Ve günün birinde şey olacak diye de bekliyorum ben. Kimse olmayacak burada. Ben tek başıma anlatıyor olacağım. O zaman da gene sorarım, sorusu olan var mı diye. İyi, yok, güzel, devam edip. Okay, so let's continue. So the next topic I would like to talk about is time to climb. So this is an important performance number. Okay, so we talked about climbing, and in climbing we used the rate of climb as an indicator of climbing performance. So it is basically half the vertical speed, right? Rate of climb is, if it's 5 meters per second, that means here the aircraft, the altitude increases 5 meters every second. So the next thing to calculate from this point is how long it takes to climb from a certain altitude to another altitude. Okay? So if we could keep the rate of climb constant, then it would be very easy to calculate, right? For example, so by the way, in time to climb, we're assuming that we're doing climbing at constant speed. Okay, so we are only considering the time to climb if you follow this path. So you just increase the speed, increase the altitude at a constant speed, because that's what we can easily calculate analytically. But as I said earlier, if you want to find the time to climb during an accelerated climb, you can do this numerically by writing a computer program, and you can do that as well. But nevertheless, right now we are only talking about this climbing at a constant speed. So again, I was saying that if the rate of climb could be kept constant at different altitudes, then time to climb would be very easy to calculate. For example, if the rate of climb is constant at 5 meters per second, that means in 1,000 seconds your altitude will change by 5,000 meters. But unfortunately that's not the case. As you climb, rate of climb decreases because the excess power changes, right? The excess power reduces with altitude. So because of that, the calculation of time to climb is not that easy. So we can use this equation to calculate time to climb. So if you look at this, this is actually a differential equation, right? dH by dt. So this is an equation that shows how fast the altitude changes with time. So we can manipulate this equation. So we can leave dt on one side and dH on the other side. And if you take the integral of this equation, the integral of left-hand side will give you the total time of the climb. So you start from 0 and do the integration up to Tc, where this will give you Tc, which is the time to climb. On the right-hand side, you perform the integration between two altitude limits. The starting limit is h1, this is the initial altitude, and the end limit is h2, this is the final altitude. on the integral here, you have BH, and also 1 over rate of climb is within this integral. So this is what I was saying. If rate of climb was a constant number, then you could take this outside the integral, and this will give you h2 minus h1, right? But unfortunately, that's not the case. The rate of climb does depend on altitude, so you have to leave this within the integral, and then take the integral together with that term. So this is what you have. If the rate of climb was constant, then we could take it outside the integral and then take the integral from h0 to h final, dh. So from here we get time to climb is equal to 1 over rate of climb times hf minus h0. But since the rate of climb is not constant, it has to stay within the integral. In that case, you can do the integration. Well, to be able to find the actual answer, you need to find an expression for rate of climb as a function of altitude, right? So you need to be able to write rate of climb as some function of altitude so that you can put it in the integral. That can be done if you just use the equations. The only difficulty there is normally you can find the excess power as a function of air density, right? So you can you put the rate of the excess power expression as a function of density, and then you need to relate density with altitude, and for that you need to use a different expression. So that's what complicates the integral. Other than that, it's not really a big deal to take the integral. So in that case, you can do a numerical integration. To do the numerical integration, you make a plot of inverse of rate of climb with altitude. So before I showed you plots of rate of climb with altitude, but for calculating time to climb, you need to plot 1 over rate of climb, and that's because that's what you have in the integral, right? In the integral, you have 1 over RC. So let me show you those plots from our last lecture. So these are rate of climb plots versus altitude, right, at different speeds. So if you want to calculate the time to climb, you need to plot 1 over rate of climb. And then you simply take the integral between 2 different altitude levels. So if you want to find the time to climb from 2 kilometers to 6 kilometers, you take this plot and then you take the integral within these limits. That means you simply need to find the area of this shape here. Okay, so this area, if you calculate that area, then whatever result you will have will be equal to the time to climb between those 2 altitudes. Okay? Okay, so there's something interesting here I would like to draw your attention to. Normally, if you ask somebody, if you ask them that I'm flying an aircraft and I want to climb a certain altitude, okay, I want to climb, let's use these numbers. I want to climb from 2 kilometers to 6 kilometers, and what should my speed be to perform this climb in the shortest possible time? Intuitively, most people will tell you that you need to fly as fast as you can. That's how you will perform the climb really fast. And if you make an analogy with driving a car, that's the answer, right? If you are driving a car and if you are coming to a hill, so you are driving your car here, and if you want to climb this hill, at the beginning of the climb, accelerating as much as possible will allow you to climb it quicker, right? But that's not really the case in case when climbing with an aircraft. That's because if you look at these plots, rate of climb plots at different speeds, you will see that there are 3 different speeds here. The fastest one is the green one, 85 meters per second. So here you are flying with the highest speed. But if you try to climb at this speed, then your rate of climb is very, very low compared to the other 2 speeds, right? So if you want to start to climb at 85 meters per second, while flying at 85 meters per second, then the rate of climb, the maximum rate of climb you can get is this much, 2 point something meters per second. Whereas if you start your climb with this speed, 30 meters per second, then the maximum rate of climb you can get is much higher. You can start climbing at 12 meters per second. And if you go back to the equations, this actually makes sense. Let's see. If you are flying really fast, if you are flying at 85 meters per second, then there will be a lot of drag force, and your engine thrust will have to overcome that drag force. And very little thrust force will be left for helping the climb. But if you are flying slowly, then the drag force will be really low, and you will be providing the full thrust from your engines, and you can get more rate of climb out of that. So anyway, if you think about the equations, you will see that if you start climbing at a lower speed, it's a more reasonable thing to do. And in fact, if you try to climb at 85 meters per second, the maximum altitude you can climb is much less than your actual up to the ceiling, right? In this aircraft, for example, if you want to climb at 85 meters per second, the rate of climb you can get is this much, but you can only reach to an altitude of about 6.5 kilometers, whereas if you do your climb at this speed, you can reach a higher altitude. So I have the inverse of rate of climb plot for this aircraft, and they are shown here. So this is 1 over rate of climb, and the horizontal axis is altitude. For those speeds, well, actually these are different speeds. So anyway, for 35, 45, and 65 meters per second, the inverse rate of climb curves are given here. So between these 3 different speeds, obviously the shortest time to climb will be achieved by the red one, right? Because we're talking about the area. So if you want to calculate time to climb from 0 altitude to 5 kilometers, the lowest area is given by this red one. And then if you perform the climb at this speed, time to climb will be the area under this red one. But if you want to climb at 65 meters per second, then you need to calculate the area under the green one, and as you can see, the area is much larger, almost twice as the area of the other one. Okay, so this is how you can calculate time to climb, and you can do the same thing to calculate time to accelerate as well, but that's not something we look at for aircraft. But şuradan alayım. Similarly, time to accelerate at constant altitude can be calculated through numerical integration. As follows: you use the same equation. So you have excess power divided by weight. So you will say that this term is equal to 0, and then you will get dt on the left hand side. On the right hand side, you will have, you can assume weight to be constant and take it outside the integral, and g as well. And then you will have v over and you can further write this as weight over gravity, v0 vf, 1 over thrust available minus thrust required times dv. Okay, so you write because thrust available minus thrust required times velocity gives power available minus power required. So the velocity, that velocity cancels this one here. And by taking that integral, you can find time to accelerate from a certain speed to another speed. In fact, you can do this analytically, I think, because you don't need to worry about going from altitude to, or air density to altitude. Here you have velocity directly within that equation. Okay, any questions? The next topic is gliding flight, which is very similar to climbing, but it's even simpler. And I was planning to cover this today, but we don't really have too much time left. So in the case of gliding, we assume that there's no thrust force. So just like a glider, in a glider you don't have an engine, so there's no thrust force. But all the other forces of flight are there. You have the lift force, drag force, and the weight. And this time you have a negative flight path angle. Right? The gamma angle is negative. In climbing it was a positive angle. So if you write the equations, you have the same equations, except that the thrust the term is equal to 0. It should be equal to 0. And by combining these two equations, you find an expression for the tangent of the glide angle, the flight path angle, and that's simply equal to 1 over L over D. And this is really all there is to the gliding flight. So if your aircraft is gliding, then the angle of glide depends on lift to drag ratio. And naturally, if you want this angle to be minimum, then you want the lift to drag ratio to be maximum. And if you are gliding, then it's natural to expect a low glide angle, right? Because you are here, you're at a certain altitude. And if your glide angle is large, then that's how you will be flying, right? This is your gamma. But if you have a low glide angle, then you can travel to a longer distance from the same height. So naturally, you want this glide angle to be as small as possible so that you can go to a long distance. So again, we see that the lift to drag ratio is a good aerodynamic performance indicator. And it's a very good number for aerodynamic efficiency. For a lot of different reasons, you want a high lift to drag ratio, and this is just one of them. So if you have a very high lift to drag ratio, then that means you can glide at a small angle, which means when you start gliding from a certain altitude, you can travel a long distance. Neyse, vakit kalmadı demiştik ama bunu da aradan çıkarmış olduk. Okay, so let me stop here, and I'm going to give you some interesting examples related to gliding. Normally, if you are flying a glider, then you're gliding at all times. But if you are flying an aircraft, and if for some reason if you lose engine power, then you have to glide. In that case, the gliding performance becomes an important performance criteria even for regular aircraft. For gliders, obviously it's the only thing they do, so that's very important, and they are optimized for gliding performance. But even for regular aircraft, you have to take gliding performance into account, because in case of an emergency, you may have to glide without the engine power, and you need to have a good gliding performance. It will be a nice thing to have. Okay. So again, let me stop here, and on next week on Tuesday, I'm going to talk about some important examples from real cases about this gliding flight, and then I will start range and endurance after that next week. Okay, so I'm going to stop here.